So what was the point of the work that we did on the integral test yesterday? The point was that because of what we know about the relationship between an integral and a sum, so for instance, if I want to know something about the sum that we're looking at here on the screen right now, it's a summation of 1 over n to the 3/4 power. If I want to know something about this, n to the 3/4, maybe n running from 2 to infinity or something like that. That if I want to know something about this, what I can do instead is I can look at the integral of the function that connects the dots, if you will. Right? Instead, I can look at the integral of 1 over x to the 3/4 with respect to x, and then just run that integral from some lower endpoint that I might or might not care about out to infinity. And that whatever the integral does, in other words, if this integral turns out to have a finite value, then the sum will also do the same thing. And the reason that this works is because of this picture that we developed yesterday, where the sum itself is a bunch of those areas of those rectangles, and then just by connecting the dots either at the upper endpoint or the lower endpoint of those rectangles with a continuous function, we can set up an integral. And that integral can either be a lower bound for the sum, or it can be an upper bound for the sum, and the only difference is where the lower limit of that integral happens to be. So if my sum is from 2 to infinity, then the integral from 2 to infinity, if its value exists, will be a lower bound, and the integral from 1 to infinity, if that value exists, will be an upper bound for the sum. So that really what I would need to do to assess whether this whether the sum converges, is I should just assess whether this integral converges. So let me take the integral on the left-hand side. The integral from 2 to whatever. We'll say 2 to infinity of 1 over x to the 3/4. Now, how do I evaluate an integral like this one? The so-called improper integral. How did we do it yesterday? Say again? Yeah, so yesterday what we did is we didn't have an infinity in that upper limit. Yesterday we were looking at a partial sum, and so instead we had an n up here. And so we just evaluated this integral as though it were any other integral. Let's find an antiderivative for 1 over x to the 3/4. What is an antiderivative for 1 over x to the 3/4? How would I find an antiderivative of that? X to the, actually I think it's x to the positive 1/4. If I add 1 to negative 3/4 in the exponent, I get 4x to the 1/4. Then I'm going to evaluate that from x equals n to x equals 2. So when I evaluate this at x equals n, I end up with 4 times n to the 1/4. And then I minus 4 times 2 to the 1/4. And 2 to the 1/4 is just some number, right? It's the 4th root of 2. So there's what I get when I evaluate this integral with an n in the upper limit. And that n, again, can stand for whatever upper limit we want to, but ultimately what we want to do with that n is what? If I want to know whether the infinite series converges, then I had better let n, I better let n tend to infinity. So that's how you evaluate an improper integral like the one that we have over on the right, is you make it proper. Right? You put some upper limit on it that is variable, some limit that we're allowed to then change, and then take the limit of this result as that upper limit approaches infinity. And of course the question is, what do I get when I take the limit of 4n to the 1/4 minus 4 times the 4th root of 2? As n goes to infinity, what happens to this quantity? Yeah, because this n to the 1/4 right here, as n gets large, so does the 4th root of n. So that term right there is blowing up to infinity, which means that this entire limit is infinity minus 4 times the 4th root of 2, otherwise known as infinity. So in other words, this improper integral, what do we say, converges or diverges? Diverges. It doesn't settle in on a finite value, so the improper integral diverges, and therefore going back to our inequality over here in the bottom left, that means that over here on the left I have something that tends to infinity. Meanwhile, my partial sums, or better yet, my infinite series, since I've let everything tend to infinity, I've let n tend to infinity here. According to this inequality, the value of my infinite series has got to be no smaller than the value of that integral. But if the value of that integral is infinite and the sum is bigger, what does that mean about the series?
Divergence to infinity?
Yeah, this sounds a bit like John Lennon when he said he was, the Beatles were bigger than Jesus or whatever. Well, this sum, this infinite series, is bigger than infinity, which is saying something. Therefore, the sum, the infinite series, diverges. So the series does what the integral does, because we have this estimate that tells us that the integral has to be bigger than the series, that the series has to be bigger than the integral, and we've just shown that the integral blows up to infinity, therefore the series must blow up to infinity. Catch that? Note that the terms of this series, 1 over n to the 3/4, those terms are approaching 0. So why does this not come into conflict with the theorem we looked at yesterday? So our sequence of terms, as n approaches infinity, is converging to 0. And yet, we've just made the claim that the series diverges. How do you reconcile this cognitive dissonance? Why is it okay for this to happen?
Because you keep on adding a 0 at a point. What was that you were talking about? You would keep adding them, and then it just finally keep adding 0, so it just keep getting the same.
We keep adding zeros, yes, quote unquote, right? If we look far enough out in this sequence, we're adding terms that are getting smaller and smaller and smaller and decreasing to 0. And yet, our series still blows up. It still diverges to infinity at the value of the infinite series. So why is that not a problem? Why doesn't this contradict something we said yesterday? Yesterday, this is what the board looked like. And we had this theorem down at the bottom that said that if a series converges, if we already happen to know a series converges, then that means that the sequence of its terms must tend to 0. And then we had the contrapositive of that, which has the same logical weight as the theorem itself, right? They are equivalent statements. And the contrapositive says that if the terms do not converge to 0, the series must diverge. But what does this theorem tell us about the example we just looked at? The example we just looked at had the sequence 1 over n to the 3/4, and its terms tended to 0. So, what does the theorem tell us? Well, if you look at the original statement, the hypothesis is that the series converges. We don't know that right up front. Right? So the original theorem tells us nothing. Secondly, we look at its contrapositive. And the contrapositive's hypothesis is that the sequence of terms does not converge to 0. In other words, it still doesn't tell us anything about this particular sequence.
An alternating sequence?
This one happens not to be alternating. Alternating is a topic for tomorrow. Alternating would mean that the terms change signs. So one's positive and the next one's negative, and the next one's positive, and so on. But all these terms are positive. Yeah?
Is it...
The first moral of the story is that just knowing that the terms of a sequence tend to 0 tells us only that the series might converge, not that it does converge. The Divergence for Dummies test is just that. It's a divergence test. The Divergence for Dummies test can only tell us when a series diverges based on its terms not going to 0. Knowing that the terms do go to 0 only tells us that the series has a chance at converging, but it is not conclusive. Again, it is a necessary condition for a series to converge that its terms go to 0, but it is not a sufficient condition. It's not enough to guarantee that our series converges, just knowing that the terms go to 0. So in the box here, we can say, well, the terms go to 0, so the series, 1 over n to the 3/4, might converge. But logicians like ourselves are not satisfied with might. Ultimately, the point of what we're doing this week is to turn that might into a yes or no answer using a series of tests. And the integral test was our first one. And according to the integral test, we had a divergent series according to the integral test, but we only knew that because we computed the integral, the improper integral of 1 over x to the 3/4, and found out that that improper integral diverged, blew up to infinity. And then because of the comparison down here at the bottom, we knew that our series was bigger than that integral. And being bigger than something which is infinite guarantees that you are infinite.
Visually?
So let's take a look at the terms of our sequence, 1 over n to the 3/4. The terms of our sequence, as we look at more and more of them, the terms definitely do approach 0.
We're talking either x-axis or y-axis.
We're talking approach 0, the values of the terms, which we would record on the y-axis, approach
Okay.
0. So in other words, the terms themselves, the y values, the heights of these dots, if you like, are approaching 0. And so if we plot the terms as points like this, they're approaching the x-axis. But if we apply the crash test to this, in other words, if we take the x-axis and we invert it so that what used to be 0 now becomes infinity, and what used to be infinity now becomes 0. So if we turn the x-axis inside out so that we can apply the crash test, what do we see?
That diverges.
So what kind of a landing is this particular series making? Yeah, I don't think I'd want to be on this plane.
I'm just being a cannonball going the opposite way.
Yeah, so our plane is coming in toward its limit, towards 0, coming in this way, except that the curve that it is using as it's doing so crashes at the origin instead of making a smooth landing toward the origin, which is what we would want to see. So according to our sort of back-of-the-envelope crash test, we believe that this is divergent. But again, the integral test is what makes that precise. It's what allows us to say for absolute sure that the sum of 1 over n to the 3/4 diverges. And the reason that the sum diverges is because the sum is greater than or equal to the improper integral from 2 to infinity of 1 over x to the 3/4. And we computed this to be equal to the limit of 4 times n to the 1/4 minus 4 times 2 to the 1/4 as n tends to infinity. And by computing that limit, we found out the improper integral diverged. And therefore, this series also must diverge. Why? Because it's bigger than infinity. And being bigger than infinity definitely guarantees that you are infinite. And that's a proof. That is a guarantee. You can take that to the bank. That this infinite series diverges because it's bigger than a divergent improper integral.